For an inverse of a function to exist, it must be one-to-one on the domain. Most polynomials are not one-to-one. For example, let's look at the polynomial y is equal to x squared plus 1. The graph of the polynomial is seen above. So this polynomial is not one-to-one because by the horizontal line test, we see that we have a horizontal line that passes through it twice. Therefore, the inverse of x squared plus 1 doesn't exist on the entire domain. But we can define an inverse for this function if we restrict it to a smaller domain so that our function is one-to-one. And in general, that's how we find inverses of polynomials. If f of x is not one-to-one, then we restrict it to a domain where it is one-to-one. And in the graph of y is equal to x squared plus 1, here's an example where the domain makes the function one-to-one. Before we look at any examples, let's recall the following fact. The domain of f inverse is going to be equal to the range of f of x. And the domain of f of x is equal to the range of f inverse. This will be a useful fact whenever we're trying to find the inverse on a restricted domain. Now let's look at this example. We want to find the inverse of f of x is equal to x plus 1 raised to the second on two different intervals. The first interval is x is greater than or equal to negative 1, and the second interval is x is less than or equal to a negative 1. We're going to break this up into two cases. In the first case, we'll be looking at the interval when x is greater than or equal to negative 1. And so this means that the domain of our function f of x is going to be all numbers that are greater than negative 1. And the range of our function f of x is going to be from 0 to infinity. To find the inverse, let's rewrite our equation y is equal to x plus 1 raised to the second, and we're going to switch our x and y's. So we'll get x is equal to y plus 1 raised to the second, and now we're going to solve for our y value. Taking the square root of both sides, we'll get plus or minus the square root of x is equal to y plus 1, and we see that we'll get plus or minus the square root of x minus 1 is equal to y. Now recall that the domain of f of x is equal to the range of f inverse, and also recall the range of f of x is the domain of f inverse. Since we want all the y values in our f inverse to be more or less positive, we're going to choose our plus or minus to be plus. So we'll get y is equal to the square root of x minus 1 as our inverse function. Now let's look at the inverse for all the x values that are less than or equal to negative 1. Again, the domain of f of x is going to be all negative values up until negative 1. And the range is still all positive values, 0 to infinity. Again, we want to find the inverse, so we'll rewrite our function first, switch the x and y's, and then solve for y. Again, we'll get plus or minus the square root of x minus 1 is equal to y. And again, recall the range of f inverse is equal to the domain of f of x, and the domain of our inverse is equal to the range of f of x. So we want all the y values in our range to be negative, which means we want to pick for the square root of x this negative value here. Therefore, y is going to be equal to a negative square root of x minus 1. And this is the inverse on the domain from negative infinity to negative 1. So notice that depending on the domain, we get different inverses. So what we see is that if we call this inverse f inverse 1 and this inverse f inverse 2, then clearly these two inverses are not equal to each other. So depending on how we restrict our domain, we'll get different inverse functions. Let's find the inverse of the function y is equal to 5x cubed plus 1. Before we find the inverse function, let's sketch a picture of the graph. This again is a cubic function that's been pushed up 1 unit and has a vertical expansion of 5. So a sketch of our graph will look something like the following. And this graph is one-to-one on the entire domain. So the domain is given by negative infinity to infinity, and the range is given by also negative infinity to infinity. So to find this inverse function, we let y be equal to 5x cubed plus 1, and now we switch our x and y's. So we'll get x is equal to 5y cubed plus 1. Then we just solve for y. So subtract 1 on both sides, we'll get 5y cubed is equal to x minus 1. Divide both sides by 5, we'll get x minus 1. Divide by 5 is equal to a y cubed. And finally we get y is going to be equal to the cube root of x minus 1 divided by 5. And this is our inverse function. Now let's go ahead and verify that the inverse of the cube root of x minus 1 divided by 5 is the function we started with. Again, we're trying to find the inverse of y is equal to the cube root of x minus 1 divided by 5. Let's rewrite this equation. We'll get y is equal to the cube root of x minus 1 divided by 5. And now switch your x and y's. So we'll get x is the cube root of y minus 1 divided by 5. And now we just solve for y. Cube both sides, we get x cubed is equal to y minus 1 divided by 5. Multiply both sides by 5. We get 5x cubed is equal to y minus 1. And finally, add 1 to both sides and we get y is equal to 5x cubed plus 1. And so this is the inverse of y is equal to the cube root of x minus 1 divided by 5. And what we just shown was that the function from the last problem and this function are both inverses of each other. There's another way to verify this besides computing both of the inverses, and we've seen this before, and this was called the inverse property. So let's go ahead and reiterate this theorem. So the inverse function property states that if you're given two functions, f and g, where f and g are inverses of each other for all x in the domain of f and in the domain of g, then we have that g composed with f and f composed with g is equal to x. Let's go ahead and use the inverse function property to verify that the function f of x and g of x are inverses. First, evaluate f at g of x. And what we're going to do is we're going to replace all the x values in f of x with a 3x minus 5. So this is going to be 3x minus 5 plus 5 divided by 3. Our 5's cancel out and we're left with a 3x divided by 3, which is equal to x. And now we need to go ahead and check g evaluated at f of x. This is g evaluated at x plus 5 divided by 3. And now we're going to replace all the x values in g with our x plus 5 divided by 3. This is then 3 times our x plus 5 divided by 3 minus 5. So multiplying our 3's out, we get an x plus 5 minus 5, which is equal to x. So by the inverse function property, this tells us that f and g are inverses.